Imagine such a scenario where n people are enjoying a boat trip. When they get to the middle of nowhere, they find that the ship cannot hold all of them at the same time and only less than half of them can stay on it. To decide who can stay, they play a game called the Minority Game. The rule of the game is everyone chooses between 0 and 1, and those who choose the minority outcomes can stay. Since the boat is sinking soon, they've only got time to play the game once. Plus, if the outcomes are evenly split or all outcomes are the same, everybody loses and nobody can stay on board. Of course, everybody wants to increase his possibility to survive. The game can be abstracted into a math model. Everyone is given a classical bit 0 and can either choose to do nothing with it or flip it into 1. Thus, the action set of each player is I or X, where I is the identity matrix and X is the bit flip matrix. To illustrate, let's see what happens if there are 4 people. That is when n is equal to 4. Obviously, the best strategy for everyone is to randomly choose between I and X. And it is easy to calculate that the probability to survive for everybody is the same, which is 1 over 8. 4 times 1 over 8 is 1 over 2, what about the rest half? Notably, there is 50% chance that everyone dies. What a disaster! Fortunately, all of them 4 have knowledge of quantum computation. Decide to play the quantum version of the Minority Game. The rule is slightly different. Everyone is given a qubit ket 0, then an entangling unitary gate J is applied on all qubits. After that, everyone can apply whatever unitary gate to their qubit. Then the adjoint of J dagger is applied to these qubits. Finally, all qubits are measured on a computational basis and the outcomes are their choices. Same as the classical game, those who get minority outcomes win. With the choice of J and unitary gates for each player as given in the video, a final state psi ket is achieved. Amazingly, the optimal strategy shows everyone can have up to 1 over 4 chance to survive. It is not hard to observe the all-death outcome is eliminated in the quantum case. The general case of the problem has n people. We present unitary gates chosen by a player as Si with 3 parameters. Notice if all bits are flipped, winning and losing results are the same, so we calculate the sum of the probability of each outcome and its flip by Born's rule. If we expand the probability and combine terms, we will get such an ugly-looking monster. Here J is the number of zeros in the outcomes. We can do the same for the flipped outcomes and get another monster with similar structures. If we combine these 2 monsters, we will get an elegant formula. It can be easily observed that when n is odd, the probability is only affected by parameter alpha and is the same as the classical case. When n is even, the probability has one more term, delta involving beta and gamma, and the optimal solution gives better results than classical ones, which means everyone can have a higher probability to survive. Well, before playing the game on the quantum machine, we suddenly realized that the machine is almost twice the weight of ours, combined, and we tossed it into the water, and everybody survived. End of story. Tee-hee!